This is session 14. Hi students. So far we discussed what is SN1 and what is the stereochemistry in SN1, which type of products we are going to get, and how products depends upon a substrate, nature of substrate. Which product you are expecting major, experimentally which product you are getting minor. What happened in case of bicyclic compounds containing less than 8 carbon atoms, where leaving group attached to bridgehead carbon and leaving group attached to some other carbon rather than bridgehead, and all other points are covered. Now what are the factors which favors SN1 reaction? Now there are mainly 4 factors. One is the nature of substrate, and second one is leaving group, and third one is solvent effect, fourth one is nature of a nucleophile. Let us see one by one. Here substrate is nothing but reactant, means alkali halide generally we have to consider. So for SN1 reaction, alkyl halide, which type of alkyl halide generally required? So SN1 reaction preferably proceeds via formation of carbocation intermediate, and that formation of carbocation is a relatively slow step compared to the second or third steps. So slow step, rate determining step, formation of carbocation. That formation of carbocation, it is bond breaking step. For bond breaking we need to provide more energy. That's why we can say first step is endothermic, means we have to supply energy for breaking of CX bond. Ultimately you are getting carbocation. So the formed carbocation, if it is more stable, so how do we know that which one is more stable and which one is less stable? That already we discussed in previous sessions. Tertiary carbocation is more stable than secondary carbocation, primary than methyl carbocation. So while forming tertiary carbocation, the activation energy required, activation energy is less, whereas for formation of primary carbocation, activation energy is more. So already we know that activation energy is nothing but difference in energy of transition state and energy of reactants. Right now reactants energy how much we need to provide in order to go to transition state. So the difference in between these two, what we call activation energy, that activation energy is very low in case of tertiary carbocation. That means we are providing less energy for formation of tertiary carbocation. In other words, we can say tertiary carbocation is holding very less energy. When it possesses less energy, then that carbocation will be more stable. Just tertiary carbocation, why it is more stable means we can explain based on electronic effects. Like in tertiary carbocation, that positively charged carbon is attached to 3 alkyl groups. That's why more plus I groups, or in other words hyperconjugation. So because of plus I or hyperconjugation, tertiary carbocation stability is more than secondary, than primary, than methyl. So reactivity towards SN1 also proceeds in the same order. Because of more stable carbocation, you are getting major product. Tertiary carbocation when more stable, then from that tertiary carbocation whatever you are getting, that product is major. So reactivity order of SN1, tertiary alkyl halides, because they can produce tertiary carbocation, then secondary, then primary, and methyl last. So nature of substrate, tertiary greater than, secondary greater than, primary greater than methyl. Let us recall for SN2, its reverse order. And strictly I am saying you are not supposed to generalize and you are not supposed to apply everywhere this statement. If SN1 order is this one, SN2 order will be ulta. So we are not supposed to say like that. You should remember this is strictly applicable up to here only. Now let's come to leaving group. So what is meant by this leaving group? The group which one leave away and ultimately produces carbocation. So how the leaving group, whether it is SN1 or SN2, leaving group must and should good leaving group. It has more tendency to leave. So how do we know that which one is good leaving group and which one has more leaving tendency? Generally with increase in size, leaving group leaving tendency increases. Suppose fluoride, chloride, bromide and iodide, if you consider F minus, Cl minus, Br minus, I minus. Obviously I minus large size, that's why iodine comes out as I minus. It has more tendency to leave compared to bromide, compared to chloride and compared to fluoride. So here leaving group leaving tendency we can expect based upon their size. more the size, more the leaving ability. That one first one. So leaving tendency, leaving group, leaving tendency obviously influences both SN1 and SN2. Irrespective of which type of mechanism, it is not criteria. Obviously it has to leave away, and whereas in case of SN2, by leaving its position, it allows the incoming nucleophile to attack upon electrophilic carbon. In case of SN1, by leaving its position, it will remain there positively charged carbon, that what we called for carbocation. So more the ease of formation of carbocation, more the SN1 we can say. That's why whatever that is SN1 or SN2, rate, both rate influenced by good leaving group. Leaving group nature is good, leaving group has more leaving tendency, then both rate will be increases. And as I mentioned that size is factors, more the size, more the leaving tendency. And the second one already we discussed, once it comes out along with electron pair, it should maintain its stability. It is not supposed to think about once again regarding that carbocation. Again I want to go there, I want to attack upon that carbocation. No, such a scenario we should not observe with respect to this leaving group. Means leaving group once departed from carbon, it has to stabilize along with that electron pair. So it must be weak base. Being weak base, it can be stabilized. Check out that HI is strong acid conjugation is weak base, so weak base and it can be stabilized. Again, once again I am repeating, previous session we discussed, it is strong acid. What do you mean by strong acid? It has more tendency to give H plus. In other words, if you think in another angle, then anyway, either of the way, it want to kick out that H plus. So it want to kick out, and in another way, it don't want to stay with H plus, and in another way, it want to exist solely. So when I minus, it can be stabilized, itself it can be stabilized in such a manner, it is going to lose its H plus. So we can say bulky, and second one, it is weak base, and third one, it has to stabilize itself with a bonded pair of electrons. And whenever all these cases are satisfied, then simply we can say that this one has a more polarizable. So being more polarizable, it stabilizes carbocation more. Polarizability, polarizing power, in previous sessions already we discussed, polarizing power is for cation, polarizability is the nature of anion. Polarizing power is for cation, we have to apply, and polarizability is the quality of anion. So more polarizable. So how do we know which one is more polarizable, which one is less polarizable? The one which has a less charge density, that one is more polarizable. So basically I minus, this I minus is going to polarize, means negatively charged one, all the negative charge comes to one direction and all the positive charge comes to another direction. In such a case, it can stabilize that carbocation. So towards positively charged carbon, it leaves a negative charge and all the positive charge comes towards I. By whenever it maintains this is such type of atmosphere, here the carbocation formed one is can be stabilized. I am repeating once again, here I minus large size, yes, large is more the size, more the leaving tendency. Second one, it should be weak base, yes, obviously it is conjugate of strong acid conjugate is weak base, then being weak base, it can stabilize and it should retain after very stable after left with electron pair. Yes, after comes out from the carbon, it can sustain, it can stabilize. And fourth one, highly polarizable. So being highly polarizable means more polarizability. Because of more polarizability here, negative charge, positive charge, within I minus, all the negative charge, positive charge comes to different directions, means polarity or dipoles are created within I minus. So by whenever it gets like that, being large size and less charge density, then it happens like this. In such a case, it can stabilize carbocation. So all these are the qualities for good leaving group. And in case of SN2, we already discussed that triflate, trifluoroacetate and brosylate, nosylate, tosylate, all these are good leaving groups. Here also all are good leaving groups. That all we can consider here also, they are all good leaving groups. And third factor, if it comes to third factor, for SN1 rate determining step, first step, formation of ions. That formation of ions happens only in case of polar solvents. polar solvents, that too polar protic solvents. There are two types of solvents in the previous session SN2 we already discussed. That is polar protic, polar aprotic, completely non-polar. Three types of solvents. Polar protic, we need them. Polar aprotic, of course better. Aprotic, not suggestible. Sorry, non-polar, not suggestible. Because of mechanism via formation of ions, mechanism proceeds polar mechanism. So here polar solvent only required. And in polar solvents again two cases, polar protic and polar aprotic. We need both, because in case of polar aprotic like chromethers, DMF, dimethyl formamide, dimethyl sulfoxide, there already we learned that solvent molecules are going to solvate only one type of ion, that is nothing but cation. So there polar aprotic solvents like DMF, DMSO, chromethers, all these solvent molecules can solvate only cations but not anions. There what happened? When anions are not solvated, then anion nucleophilicity enhanced, and that enhanced nucleophilicity, anion attacking ability enhanced, increased, right? Now here we need polar protic solvents. Why polar protic solvents? Here both cation and anion need to solvate. So Rx, alkyl halide, which upon dissociation you are getting R plus and X minus. Now these R plus ions are surrounded by water molecules like solvent molecules. I am going to consider water as solvent. So polar protic, which are able to form hydrogen bond like ammonia, alcohol, water, like that. Of which we have to, which one we have to opt, that we will discuss little later. Let us assume water molecule I am going to take as solvent, and because of these cations and anions, all these are gets solvated. More and more number of solvent molecules are surrounded around this cation and anion, which makes the formed cation and anion are more stable. In previous session already we discussed that there is first direct breaking R plus R minus, it won't happen. Initially what happened? This X is going to pull its bond pair of electron, and there will be a formation of partial negative charge and partial positive charge. And slowly that negative charge upon halogen or leaving group and the positive charge upon halogen containing or leaving group containing carbon slowly developed, and their charge, with increase in their charge, parallel to that there will be attraction, electrostatic force of attraction increases. That's why whenever the charges more and more developed upon both leaving group and carbon, leaving group containing carbon, so more and more charges developed, what we are expecting, it will leave away, but it won't leave away. What happened? Intimated ion pair formation takes place. Intimated ion pair, if you convert into solvent separated ion pair, of course we are not supposed to convert, that has to perform by solvent molecules. In order to perform that step, solvent molecules must and should be polar. That's why polar solvents only favors SN1. Polar solvents only favors SN1. Here once R plus and X minus both ions are formed, this R plus will be solvated with water molecules with oxygen phase, which bears actually negative charge. Negatively charged phase containing oxygen atoms of water molecule, and X minus surrounded by positively charged phase of hydrogen atom of water molecule. Of course both are solvated by water molecules. So whenever solvent is polar, it possesses both plus and minus. So they can solvate both cation and anion. This step what we are calling solvent separated ion pair. Whenever intimated ion pair converts into solvent separated ion pair, then in such a case, then next step means attacking of nucleophile upon positively charged carbon happens. Otherwise you are getting only inverse now product. Let us recall once SN2 what we discussed. There we are using polar aprotic solvent which is solvate only cation but not anion. So nucleophilicity increases, that we discussed. So for SN2 you may get SN2, you may need only polar aprotic, but for SN1 polar protic. Fine. Polar protic solvent solvates both cation and anion. That is clear. Now which solvent is better? The one which has high dielectric constant. The one which has high dielectric constant, that one is more favors SN1. So high dielectric constant, generally water 78 and methyl alcohol 33 dielectric constant value. Ethyl alcohol, see water HOH. So methyl alcohol CH3OH, instead of hydrogen one alkyl group, one methyl group came here, and ethyl alcohol, instead of methyl 2 carbon containing alkyl group. So it is very clear, as the number of carbon atoms in alkyl group increases, their dielectric constant increases. And acetone 21 and hexane, which is non-polar, and it has dielectric constant 2. That means more the dielectric constant of solvent, more the polarity, we can say, more the polarity of the solvent, more the, it favors more for SN1. Let's come to nucleophile nucleophilicity. Simple. Whether it is SN1 or SN2, nucleophile must be good. Good nucleophile only attacks, it has more tendency to attack upon positive charge. Whether it is partially positive charge from rare side in case of SN2 or completely positively charged carbocation in case of SN1. So whether SN1 or SN2, first of all, nucleophile must be good nucleophile. Remember that I am saying that good nucleophile, but I am not saying that strong nucleophile. There is a lot of difference in between these two. I need good nucleophile, but I don't need strong nucleophile for SN1. Underline this point, we will discuss little later. Now, here SN2, SN1 rate of reactions, if you notice, in case of SN2 rate law we learned as R is equal to rate of reaction is equal to K rate constant into concentration of substrate and concentration of nucleophile. So SN2 reaction obviously influenced by concentration of nucleophile. So if we increase the nucleophile concentration, reaction rate increases. That we learn in case of SN2. But here we need to discuss regarding SN1. So for SN1, what is rate law? R is equal to K into substrate. So in rate law of SN1 reaction, there is no concentration of nucleophile term. Since there is no concentration of nucleophile, that means concentration of nucleophile do not play any role. Do not play any role means nucleophilic concentration is independent. Nucleophilic concentration is independent for SN1 reaction. Concentration means whether it is 0.01 molar or 0.1 molar or 1 molar, it's not criteria. Whatever the concentration you are using, here SN1 rate is not going to change. And in SN1 reaction, we preferably used alcohol as a nucleophile or a neutral nucleophiles rather than charged one. Neutral nucleophiles rather than charged one. And once again, we are recalling that point. Compared to neutral, negatively charged nucleophiles are strong nucleophiles. And I am saying that here not charged one, neutral one means weak nucleophiles. So weak nucleophiles, generally weak nucleophile favors SN1, strong nucleophile favors SN2. Weak nucleophile favors SN1, strong nucleophile favors SN2. Let us see CH3OH, which is a neutral molecule, and CH3O minus, which is charged one. It is very clear, being a neutral molecule, less nucleophile, or we can say weak nucleophile methyl alcohol, methoxide ion is strong nucleophile. When we are using strong nucleophile, this one favors or this one promotes SN2, and weak nucleophile promotes SN1 reaction. So here SN1, SN2, weak nucleophile promotes SN1, strong nucleophile promotes SN2. Now, sir, you only mentioned in the beginning of the reaction as whether it is SN1 or SN2, nucleophile must be good. And there only you gave an instruction, I am going to say good nucleophile, but I am not going to say strong nucleophile. So what you are saying, CH3O minus when we are using means strong nucleophile, if we are using, then SN2 reaction do not takes place. Yes, SN1 reaction do not takes place, only SN2 takes place. So when what happens, sir? Okay, I am not going to provide SN2 conditions. I am giving only polar protic solvents. Okay, fine. So polar protic solvent means, let us assume water molecule you are using as solvent, accepted. Tell me. And I am using CH3O minus. Okay, CH3O minus you are using as a base. That means nucleophile. Okay. So when we are using a nucleophile CH3O minus, alcohol, instead alcohol or what we called H2O as a solvent, and a tertiary carbocation I am going to use, then it leads elimination. It leads elimination rather than substitution. That we will discuss in next session. So, what I said, CH3OH is a weak nucleophile. Being a weak nucleophile, you are not supposed to expect any SN2 product. It promotes only SN1 product. And CH3O minus, it is a strong nucleophile, and being strong nucleophile, strong base also. Being strong nucleophile and strong base, it promotes SN2. And if you try to perform SN, if you try to get SN1 product, you are not supposed to get any SN1 product. Instead of that, you are going to get elimination products. Remember that, keep that in your mind. Now, if a substrate is secondary and tertiary, so okay, I am going to take one more condition, sir. So here secondary and tertiary, obviously they are able to form more stable carbocations. In such a case, even though nucleophile is weak, obviously they promote SN1 reaction. That is clear. If a substrate is secondary or tertiary, in such a case, they are able to form somewhat stable carbocation in case of secondary, more stable carbocation in case of tertiary. That's why they are able to form carbocations. In such a case, a weak nucleophile when we are using, obviously they are promoting SN1. Okay. Now I don't want to use like that. I am going to take a primary alkyl halide. I am trying to use a weak nucleophile, primary alkyl halide. Okay. Primary alkyl halide, are they able to form any carbocation? No. But there is a possibility. I think in previous session we discussed, even though primary carbocation is unstable, its formation takes place if there is any scope for rearrangement or ring expansion. In such a case, possibility is there. But there is no such case, sir. There is no rearrangement or ring expansion. Only primary alkyl halide I am going to take, and I am going to use weak nucleophile. Okay, fine. What reaction? SN1 or SN2? No reaction. If you are using weak nucleophile and if you are considering primary alkyl halide, so you only said that it is weak nucleophile, its nucleophilic tendency is very less, and unless carbon bears complete positive charge, it cannot go and attack there. And you are considering primary alkyl halide, their halogen cannot depart completely, carbon is not going to allow because of primary carbocation is highly unstable. Or in other words, we can explain, in order to break that CX bond, we need to provide much more energy. When you are providing much more energy, that carbocation formed one is highly unstable. So such a reaction do not takes place. And you think one more thing. One bromocyclohexene, 3-bromocyclohexene. This one gives a secondary carbocation. This one gives a secondary carbocation. If I am going to keep here methyl group, how many products you are going to get in SN1 mechanism? So let us consider solvent is H2O and heat SN1 conditions only I am giving. So how many products you are going to think you are going to get? Think about that answer.